Hey everyone. So what we're gonna do for this one is we're gonna look at the. I'm gonna go through the answers to the magnetism practice sheet. Once you do this, you should be all set to take the quiz. So just do that. Make sure you're looking at the other file, the one that says magnetism unit quiz, and answer that one through the Google Classroom. Okay. So for this, again, the answers are all the way on the last page of the other PDF, of the one that I gave you. So double check your answers, and for this, just skip around to the ones you got wrong. I'm going to go through all of them, but again, just jump around to the ones that you had trouble with. Number 1, moving a length of copper wire through a magnetic field may cause it to have a. So for this one, the important idea is that electricity creates magnetism, and magnetism creates electricity. So if we move the wire through a magnetic field, we've got a changing magnetic field that can create electricity. Out of all of these, which would create electricity? Well, the answer to this one is A. You may remember that potential difference means voltage, and voltage is what pushes charge. So that would be our answer here. Magnetism doesn't create temperature, doesn't resistivity, you may remember, depends on the material, so it won't change the material, and it won't change the resistance because it's the same object. Changing resistance does not create electricity. So that's that one. Alright, next up, we're going to draw a magnetic field. It says draw at least 3, so if this was the regions, assuming we have one, again, make sure you just follow the instructions here. Magnetic fields always point from north towards south, and mine look atrocious, but that's it. Just from north towards south. There you go. Which particle would produce a magnetic field? Okay, to create magnetism, the important part, if you watch the video, I really tried to make a big deal out of this, is that it must be moving charge. Moving charge creates magnetism. So let's go through all of these and let's see which one fits this description of moving charge. A neutral particle? No, that's not charge. A neutral particle? That's not charge. A stationary charged particle. I like that it's charged, but stationary is bad, right? It has to be moving charge to create this. The answer is D. So if you remember that idea, moving charge creates magnetism, you'll be good. The diagram below shows the magnetic field between two poles, A and B, which describes the polarity. Okay, so for this one, magnetic fields always point away from north and towards south. I think they're pointing away from A, so A must be north, and then B must be the south. Notice that it looks, really similar to the diagram from 2, so it does actually have to be that same setup. A is a north pole, B is a south pole. Magnetic fields are produced by particles that are, again, I'm just trying to make a really big deal out of this. Moving charge creates magnetism. That's number 5. Number 6. Hopefully this kind of just looks familiar from the diagrams from the note packet. We point away from north and towards south, and it has to, again, point towards south, so the arrow's like that. If it says a minimum of 4, which it does right here, even though I just drew all over it, there we go. Try not to let them cross. I know it's hard on the computer with my stylus, but that's what I try. 7. In order to produce a magnetic field, an electric charge must be moving charge creates magnetism. It can be positive, it can be negative, but it has to be moving. Alright, which type of field is present near a moving electric charge? Wow, this sounds like the same thing I've been saying. So we definitely have magnetism because the charge is moving. So it's not this one because, again, a moving charge definitely has magnetism. And it's not this one, because it says neither. So that one's wrong. Now, charge is always surrounded by an electric field, because it's charged. Like, positives have the field pointing away, negatives have it pointing toward. So all charge has an electric field. So the answer to this one is C. All charge has an electric field. All charge has an electric field. If the charge then moves, there's an electric field and a magnetic field. So there's always an electric field around a charge, and then if it's moving, there is also a magnetic field. The diagram represents a bar magnet. The direction of the magnetic field at point P is toward. So I'm just going to draw in the field, and we'll take it from there. So I'm going to draw it kind of pointing like this way. There we go. Now it says at point P, which is right here. like right here. And I would say that if you sort of followed along, I would say it's pointing kind of more or less towards the right at that instance. Which in this diagram is towards point C. Which diagram represents the field near a bar magnet? Again, I keep asking this one because I wanted to just start looking familiar. Always, these two look wrong, right? They're just like the wrong shape, C and D. Out of A and B, they look the same, but one of them has the correct arrows, and the one with the correct arrows is B. Always out of north and then towards south. 11. The diagram represents lines of magnetic flux. I didn't cover this term, but it just kind of means field. And that's all really. That's all it means. Within a region of space, the magnetic field strength is greatest at point. So the fact to remember here, in the note packet, it was the second rule for fields, is that the closer the lines are, the stronger the field is. Closer the lines are, the stronger the field is. And I think the lines are really close together here. So I went with B. Close lines means strong field. The diagram below represents a 0.5 kilogram bar magnet and a 0.7 kilogram bar magnet, a distance of 0.2 meters between their centers, which represents the forces between the magnets. Alright, looks like it mentions gravitational and magnetic. And let's start with, let's start with gravitational, because it's a little bit easier almost. Is gravity attractive or repulsive? For this one, gravity is attractive. Gravity is always, always, always attractive. Think about just everyday life. You've never seen an object repelled from the Earth by gravity. It doesn't happen. Because gravity is always attractive. So, this one says gravitational force and magnetic force are both repulsive. That's wrong, because again, gravity is attractive. Always. Gravitational force is repulsive, so B is wrong, because gravitational force is repulsive. That's a wrong statement. Alright, so these both say that gravity is attractive. We're between C and D now. The magnetic field, the magnetic force, it depends. Opposites attract, likes repel. I'm looking at two like poles next to each other, right? Two of the same poles. Opposites attract, but likes repel. The answer is C, because two of the same poles are near each other. If opposites were near each other, then it would attract. Two more. A little wordy here. A magnetic compass is placed near an insulated copper wire. When the wire is connected to a battery and current is created, the compass needle moves and changes its position, which is the best explanation for the production of a force that causes the needle to move. I'm hoping this sounds familiar from one of the videos that you watched during the note packet. It was one of the videos I assigned where you had the wire, and then we connected the battery, and then the compass, which was next to it, changed direction. So out of all of these, what are we going to go with? The copper wire magnetizes the compass needle and exerts a force. Okay, so magnetizes the compass needle. I don't know about that. Let's look through all these. The compass needle magnetizes the copper wire and exerts a force on the compass needle. The insulation on the wire becomes charged, which exerts a force on the compass needle. The current in the wire produces a magnetic field that exerts a force on the compass needle. This one I'm looking for you to go with D. These are kind of just word soup, a lot of them. They're not really what's going on here. But current, which remember is moving charge, creates a magnetic field. And that's the idea here. That moving charge creates a magnetic field, and that's what pushes the compass. 14. Which diagram represents magnetic field lines between two north poles. Alright, these are two like poles. So these two are going to be the wrong shape. And for the two like poles, they both come outwards, right? Remember we did the north, and they had that shape. From there, it's going to be one of these two. And remember, magnetic fields always point away from north. The answer is D. Okay, so that was some quick practice. At this point, you should try the quiz. For the quiz, just read through it, answer it on the Google Docs. A couple of questions are exactly the same as these ones, so feel free to look back, and it's a couple of free points on that quiz. But if you get stuck on the quiz, actually just email me and I'll help you out with it. That's it.